Hello everyone, it's great to see you again in the second part of California wildfire hotspot detection tutorial. I'm excited to see you. In the second part of the tutorial, we are going to use the California wildfire dataset which we have created in the first part, and we are going to apply various machine learning algorithms through different machine learning libraries and build a machine learning model so we could detect the wildfire hotspot scattered all around the California. This tutorial is divided into two key parts. First, we are going to discuss our machine learning strategy, and using this strategy, we are going to feature engineer our California wildfire dataset. The feature engineer dataset will be used for the second part of tutorial, where we are going to use the LightGBM, xgboost, and H2O.ai open source machine learning platform to build machine learning models. These models will help us to identify the wildfire hotspot, and that is what the objective of our machine learning exercise. Combining part 1 and part 2 of these tutorials, my expectation is that anyone who is following these two-part tutorials can not only has ability to collect the worldwide wildfire data, but also has ability to predict the various wildfire hotspot for whatever country or the region they are trying to work in their problem. Once again, I appreciate your time. If you like content, please feel free to share and subscribe it, and let's get ourselves started. So in the first part of this tutorial, we have learned how to generate the data set related to United States as well as the California wildfire, starting from year 2000, all the way to year 2022. And very recently, I have also completed the year 2022, January, February, and March 25th. So we have all the data for United States as well as for the California. So if you are interested to learn more about learning how to collect the data and all around it, please visit this tutorial. This GitHub repo related with wildfire already has all the data related with overall this project. So the data set, we have all these Jupyter notebooks, which talks about how to collect the data and how to make sure that we do have appropriate data required for wildfire problem. The machine learning work we are going to do is the Jupyter notebooks will be available in this ML folder, and the data set which we are going to apply in today's lab or the tutorial, that is also located here. It's a California daily data, and if you would want to just directly use the training, test, and the validation data, that is also available, and all of this data is available in the zip folder. Along with it, I have also added this United States as well as the California wildfire data at the Kaggle, starting from year 2000 all the way to March 25th, 2022, and all that data is also available here. So the data set which we are going to use in this tutorial in this Jupyter notebook is the data set that is CA daily fire 2000 all the way to 25th March 2022. The data set is also available in this California data folder here, so you can download it or you can access it directly from the pandas read CSV, or the data is also available at the Kaggle, which you could download directly from here. So there are various ways you can collect this data set. So this is our Jupyter notebook which we are going to use in this project. So before we start looking into the data set and talk about machine learning, let's try to understand what is our strategy to work on this California wildfire problem. So here, as you can see, that our original data belongs to California wildfire has these key fields. It has date, it also has the longitude and latitude along with the confidence, the satellite from which this data set was collected, and the instrument which was onboarded that satellite, which really calculated this wildfire data value and created the confidence. So that is our original data. The first tutorial really talks about a lot more in depth about this detail. And because the wildfire problem is mostly goes with days and month, so we are not taking the resolution of the time when this data was collected. So that's for that reason we are not looking into the acquired time. We are focusing on acquired date. So there are two things we do at very early stage. Very first, we take the date and we extract the year and the month from each date. So now we have wildfire data which is based on a particular year and the particular month. Second thing what we do is that we take the longitude and latitude data which is available in up to 6 decimal digit precision. We make that data and we try to reduce it up to 1 decimal degree. So 1 decimal degree equals to around 10 square kilometer area. So if we have the fire values or the fire indicators based on longitude and latitude, we merge them together up to 1 single digit decimal precision. So that special resolution gives us for per record is about 10 square kilometer fire area. So that's what we do, these two processing at very early stage, and that generate this first level workable data in this problem. Next, after we have the data at our disposal, next thing what we do is that we try to group by the data based on year, month, longitude and latitude. So when we try to group by this data based on that, the result gives us the total number of fire count depending on single decimal precision longitude and latitude and year and month. So we get the number of fire available in that year and in that month, and using that fire count, now we have a way to understand that for a given location in the 10 square kilometer area, how many fire has happened in last 20 years. And then we can also generate a pattern that if there are fire happens on every year, if happens in the same year or every year, what month they mostly happen. So based on this data processing or this kind of data engineering work, we can collect the fire count yearly and the fire count in the same month by looking into the single decimal precision longitude and latitude. And that what gives us the fire count value depending on yearly and monthly resolution. Then, because we are trying to make this fire prediction problem in a way, is that we believe is that if there is a fire happened in a certain area, there is a high possibility that the fire is going to happen there again. And if that will be the case, then we use this new target variable which we call fire, and if the fire happened in a certain area in last 20 years about 2 or more than 2 times, then we make this target variable as true. Or if the value happens once, then we believe that in last 20 years, because the fire happens only once over there, so there is a very low probability for the fire to happen again. So the overall thesis in this exercise is that if the fire happened there 2 or more times in a certain area depending on 10 square kilometer resolution, we believe that there are higher degree or higher possibility or the higher probability for the fire to happen again. And that is the whole logic behind this exercise or machine learning exercise we have. So once we take this strategy in our account, now it is a good time for us that we can start looking into our feature engineering work based on the data set. So now we understand that our data set is the temporal data because it starts from time 2020, year 2000 and all the way till March 25th, 2022. So our data set for the machine learning, it has the temporal split, it has the time factor built into, and then the way we have decided is that we are using the data set starting from 2000 all the way to 2019 is a training data set. We use year 2020 and year 2021 for the validation, and all the data we have last 3 months in year 2022 in January, February and March, we are using that data for testing data set. So this is our temporal data set split, and next we do the feature engineering. So we have already talked about in our strategy that one strategy is that we take the longitude and latitude and set the spatial resolution to one single decimal digit that gives us the about 10 square kilometer grid. And second, we aggregate the data based on monthly fire and all the recorded locations based on 10 square kilometer grid. So that gives us the fire count, and we create a new feature name called fire for the exact location if within the 10 kilometer grid has 2 or more fire in the past. So this feature will be the binary target. So these 3 feature engineering and including the data set, this is our strategy we have already talked about. So now we can start working. And before I go deep into the more details in this tutorial, I would like to give you these 2 resources where my exercise is built on. These 2 resources are the Spot Challenges Wildfire from the IBM, and the second is the Wildfire Challenge from H2O.ai. So this exercise is heavily dependent on Australia Fire Prediction, this Jupyter notebook from H2O.ai, but rather than using the Australia Fire Prediction, we are using the United States and especially the California data set. So that's a big difference, but majority of the exercise is totally dependent on how this Australia Fire Prediction kit is created. The exercise which is used by the IBM has a little more to it. It means they are using the weather data where the wind, precipitation, rain, all that thing is included into the data set. So all the wildfire data along with the weather data is combined for the machine learning model prediction for the wildfire. So that will be the part of next tutorial. We are not going to take the weather data in the account. We are going to focus mostly on the United States, especially the California wildfire data, and we are using the probability of a fire if happened in past, then it has higher probability to happen again method in this exercise. So please do visit to these 2 resources, and they are also added here. So please make sure that you do visit and you learn more about that, because that is definitely going to assist you. So we are going to import various pandas, NumPy, matplotlib, plotly and libraries which are required for this project. So here are a list of libraries which are needed for this project to work, and mainly we are using pandas, NumPy, datetime, matplotlib, plotly, colab and xgboost. I already have this California fire data located in my local machine, and just once again, if you would want, you can get the data directly from here, or that data will be available in the same GitHub repo where you will find this Jupyter notebook. So it just shows the head, so how that data really look like. So you have latitude, longitude, acquire date, satellite, from which satellite and from which instrument, the confidence, which year and which month. And as you could see here, that longitude and latitude data is up to 5 decimal precision. So we are loading that data, and while parsing the data into the acquire date column, we can look into that the California data set we have, it belongs to the start date 2000 and all the way up to 25th March 2022. This data set has about 1.1 million rows and 8 columns. This is a sample data just to take a look. So there will be the 3 satellites and 2 instrument, MODIS and VIIRS. And confidence value will be between 50 to 100, and year is 2022, 2000 all the way to 2022, and month from 1 to 12. So what is a precision 1? Precision 1 is same thing what we have already talked about, that we are taking the 10 square kilometer area. So precision 1, and then we are making sure, the latitude and longitude is set based on that. So we can use this California data set and check it out, and you can see that our latitude and longitude is set for 1 single decimal digit precision. In the next step, we are grouping by this data for the latitude, longitude, year and month. That is part of our strategy. So we are doing group by. We have already set up the resolution here, and then we are grouping by this data. And as you could see here, that we have a new empty column created that shows that for the month and for the year, for the month, how many fires are there. So total count of fire is added. So the empty column name which is available here, we are calling it empty column as a fire count. And this data set has about 58,000 rows. It means there are 58,000 fire happened at 10 square kilometer grid, depending on year and month, but totally in last 20 year, 2020, actually 21 plus year. In last 21 plus year, there were about 58,000 wildfire in the California. It's just a sample data. And as using the number of units, you can understand that the latitude and longitude, these are the longitude latitudes we found, 23 year, 12 month, and total fire 866. If checked, if there are any empty, we do not find any empty data. However, we are looking into the latitude and longitude. If there are any duplicates, we are going to drop those duplicates, and here you are going to find the based on latitude and longitude coordinate, there are about 5,000 rows. Same thing we are doing for year and month. We are dropping the duplicates, and for year and month, this is what data we really have. So for every year, wherever in which month there were fire, that is all recorded here. So if you have 23 year times 12 month, that really gives you the resolution of number of rows. Then what we are trying to do is that we want to merge this data set. So we have this longitude, latitude, and we also have this fire times when between year and year, year and month when this fire happens. So now we need to merge these two data sets. And currently we do not have a common field in this data set. So how we could do this merge is that the best option is that we take a common feature and we add into the both data sets. So in that way, if we do this and if we try to look into coordinate, we have a common feature added. And if you look into the fire times, we also have this added. So if we have this kind of data set where there is a common feature available, a common column, then we can merge it. So what we are trying to do in this next step is that we are trying to merge this data set with this data set, and the join is our outer join, and the column or the feature which we are trying to merge, we just call it common feature. So common feature, I named it so you can understand that that's a common feature we have created between these two. So that will become our base data set. And if you look into what that base data set look like, and this is what it is. So depending on year and month, and for the longitude and latitude, now you have 1.2 million records distributed across 5 columns. And now what we are going to do is that we will take this and we will merge this data. So if you remember the total fire, so total fires data we already have, earlier we have created, and that's our total fires. So here you are getting the fire count data, which is also based on longitude and latitude. So the next step for us is to take this total fire data and do the left merge. So we are doing the left join, and we are using these 4 columns. So let's perform the join, and the history gives us 1.26 million rows. As you look into 1.26 million rows, which we have created here. So this whole data frame which we have created based for every longitude and latitude on single precision, for the month and year, we are adding that for that month and year how many fire counts happen there, and that's what you are getting from this join. And if you are interested to look into this data set, this is what history look like. So now you are seeing here that fire count for certain locations, you are someplace there are 3 fire counts, some place there are 14 fire counts, and some place there are no fire counts. So now if you look into how many NaN or missing values we have, and if you look into, they are about 1.2 million are the missing values overall. We will fill all those NAs as a 0. Look into our data set. So wherever the NaN was, we have filled the zeros with them. Now we can figure it out how many fire counts are there. So 101.2 million are the fire not happen. About 21,000 fire happen once, and there are the high fire area where the 10,000, 5,000, 3,000, and these are the places where the fire happen more. And now we are going to use this target method. It means if the fire count was 2 or more time, then we will make it binary true 1, otherwise it will be 0. So that's why the minimum fire record equals 1, and we are creating this new fire column, and based on given record we have got this. We can actually look into history. This is what our data set look like, and here is our fire column. If we want to know that how many zeros and ones are in our base data set, we can take this history value counts, and we need to select fire, and it shows that about 58,000 are the fire happened, and about 1.2 million fire not. Here is our mean for overall data set. At the next step, we are taking these 3 columns, longitude, latitude, and year, and using this fire count and fire, and generating the yearly mean as you are getting this. So here, based on these 3 fields, we are generating the total count and the fire total count, how many fires, and the true and false fire at yearly level, and same thing we are doing for the year and month here. So difference is here and here is that we are adding month also in the group by list, and here is our monthly. So for the year, that's our record 113,000, and for the year and month is about 1.26 million. Same way. Let me split this into, so that will be easier to understand. So here you are getting the year wise total fire count based on year. So here what we are doing is that we are taking this yearly fire count, and that's where our last year. So this fire count is basically the year count and the fire happened last year or not. So we are renaming those columns properly, and that's what you are seeing here. Same thing we are doing exactly for the month and renaming the fire count last year same month and fire last year in the same month, true or false. So now we have the year last year and the last year month data set available. And here is our past data set where we took the yearly data set and added a common feature, because now what our next step will be to merge these two data set. So here is our history data set. We have common feature and we have yearly common feature. It means if we would want, we can merge it. So first we are duplicating anything in our history data, or if there are duplicates, and then merging past data set which we have just created, which has the total fire count year base, and they're on these three fields, and that's our past data set. So here we have longitude, latitude for year X, because there are two separate year values in each one, and then the total number of fire count and fire happened last year or not. Let's take the past value, and now we are if past year X and year Y. So if the year Y and Y was our next one, means the right side one. So if the right side value is the higher than the previous one, and that's why that record will be in our list. So that's why out of 2.5 million record, now you are getting about 1.2 billion record. So that filter happened. Past we are grouping by, now see what past left now, about 1.8 million rows, and fire count is there, fire happened or not, and year Y. So these are the, we don't really need the previous year, we are just taking the last year when the fire happened. These columns we are renaming them properly. So latitude, latitude, longitude, year Y became year, fire count before and fire before. True or false, fire before and the fire count. That's our data set look like now. Now the base history data overall plus the past data. We are merging these two, and fields are latitude, longitude and year. So left join, and so past data, now we just need to merge the year and monthly data. So same X is growing. So at this point, if you look into the X, we have this, then we are adding one more X, two more column added, and let's add one more. So this is the last year month merge, and this was the last year. So monthly fire happened previously and the count, and yearly fire happened and count. And if we look into the X columns, and let's try to get the X, and there are 13 columns. So we have added last year same month, last year same month, last year happened or not, fire count earlier. So that's all our data set. At this point we do not need our common feature column, so we are dropping the column feature here. Now if you want to see how the X look like, this is your X, total 1.26 million rows, similar to our previous data set, and 12 columns. And here we are grouping by on year, so you are getting results. So this is the final data set which we have created based on our strategy. So X is the final data set. At this point, we can split the X data set depending on our split strategy. So all the year value from 2000 all the way to 2019 will be used for the training. 2020 and 2021. So bigger, higher than 2020 and equal 2020, and lower than 2021 and 2020. So this is like 2021 and 2020, and then the test data will be anything in 2022. So we are splitting it. Now we can do a count based on year. So this is what you are getting, count based on year for the training data, for the validation data, and for the test data. So here you could get good idea of 2001 to all the way to 2019, 2020 to 2021 and 2022. At this point, if we would want, we can save this data to the disk. So now we have training, validation, and the test data for the California wildfire, and that is saved to the disk. We can validate these 3 files are saved here. We can just take a look the number of records. So about 14,000 record in the test data set, 117,000 record in the validation data set, and about 1.07 million records we have in the training data set. Yearly fires, we can look into how this yearly fire look like, because this is just for graphics. So thus job is overdone. However, if you would want to visualization, so here is our yearly wildfire grouped by year and month. Year, month, total number of wildfire, and here you could see that we are wildfire hotspot detection in California. So which month fire mostly happens? As you could see here that June, July, August is hot time when fire mostly happen. December and January very less fire, so it proves our general assumption related with fire in California. Next, we are taking the longitude and latitude, and we are summing the total number of records, because what we want to do is that we want to generate the graph based on longitude and latitude to show that which areas are the hotspot within the California. So we want to take the longitude, latitude, and then at particular 10 square kilometer, how many wildfire happen. So that proves that for this, how many wildfire happen for that longitude and latitude, and using the mapbox and the matplotlib dataset, we are creating this xgboost mapbox, and that should give you an idea that in the California dataset, these are the hotspot depending on number of fires in last 20 years. So that should give anybody an idea that how the records really look like in terms of wildfire, or where are the hotspot in this California regions where there is a high probability of wildfire to happen again and again. So we have looked around this whole feature engineering Jupyter notebook, and we started from very early our original source data set, and finally we generated our feature engineer data based on this strategy. So that strategy is what we really have, which we are using in this project to perform the machine learning. So once we have training, test, and validation data set is ready for us, that is here we have saved it. So we will go into the next step where we are going to use machine learning library and algorithm to perform the machine learning based on our fire happen or not, because we do have binary feature based on these hotspot, and that's what we will do in the next step. This whole Jupyter notebook is also going to be available in this Wildfire GitHub repo ML location. So please feel free to use this Jupyter notebook to follow the exact same method what we have followed in this tutorial. Now that our train, validation, and the test data set is ready after the feature engineering, so we are going to start the machine learning exercise now. I already have two Jupyter notebooks ready at my Google Colab. One where we are using the LightGBM library to perform the California hotspot check for the wildfire. And then I also have another Jupyter notebook which is using xgboost. And I will also include H2O.ai open source machine learning platform. So we are going to use 3 different algorithms to perform our machine learning exercise. So let's open the very first one. And here we are using xgboost. Here we are using LightGBM. So we are importing the LightGBM and just pandas. And in case if you have to upload your train or test files, then you could use this particular cell to upload all the files, because as you could see here, the runtime where this Google Colab is running, there is no data set. Because I have already uploaded the train, valid and test data set, which we have created earlier in this feature engineering exercise when we have saved these 3 files here. So those files are already uploaded to our GitHub in this California data. So I'm accessing these 3 URL directly from here. So our train source, valid source and test source, these 3 files are actually coming out from here: train, valid and the test file exactly. So we are loading train, valid and test. So all three files are loaded. Train dataset 1.7 million rows, valid 117 and test about 14,000 rows. If you would want to group by the train values, we can see that is from 2000 all the way to 2019. Test we have 2022 only, and valid has 2020 and 2021. So these are the 3 splits we already had earlier based on our temporal data. So as you could see here, that any of our data set, if we try to choose the train columns, so we have all these data set, but for this project we are just trying to reduce the features from about 11 all the way to 9. So these are the features which we are going to use here, and for the LightGBM requirement, we are setting up the training data object and valid data object. So it uses the LightGBM dataset type, and we are selecting the train features and the train.fire. So this object has all the data frame minus the fire column, and this label has train.fire. So same thing goes with valid data. So we have defined train data and valid data. These are the LightGBM dataset objects. Now for the LightGBM algorithm, we are defining the parameters. So leaves about 10, max depth 8, objective is a binary, so our classification is binary, and metrics we are using the AUC, and the number of rounds are 500. So these are the definition for our training method. Parameters will be used and training data will be passed. Total number of rounds 500 iterations will be happen for our model training, and we are passing the valid data set which is defined here. Early stopping 5 round. It means if there is no progress happening after 5 round, you can stop the process. Our training has started, and every 50 rounds the results are available for us, and our training is completed. So our validation is about 93%. Now we are going to use the test feature. So depending on our test data set, we are using this model, which is the LightGBM model, to generate the predictions. So our predictions for about 12,000 record has been 14,000 record has been completed. Now we are going to calculate the AUC, so area under the curve. So for the test data, we have about 97% accuracy for this data set, which is very good. And now we will use this metrics.roc curve, which is the scikit library. So that should be able to show you that how our Wildfire Hotspot model performance for the 2020 hotspot we are saying, because we are categorizing a particular 10 square kilometer area will have probability for the fire or not. So for that reason, we are calling it Wildfire Hotspot. And as you could see here, that using the LightGBM algorithm, we were able to create this machine learning model. Now you can export this model and you can look into a particular area, and then you can just pass the longitude, latitude, and depending on your requirement, you could check that whether that particular area is going to have the hotspot probability or not. Because we already have majority of data for last several years for that, for overall California wildfire data set. So it would be very easier to come up with an application where we could just point out that in a map that where is, if there could be, if this particular area will be the hotspot or not, and using this model it can be defined or it can be pointed out. So that's all we had for this LightGBM algorithm or LightGBM library based machine learning model for our California wildfire hotspot detection. Next, we are going to use the xgboost. So this Jupyter notebook, I will save it, and I will also export this Jupyter notebook to Wildfire GitHub repo and in this ML folder. So let me export it. So because I already have my Google Colab connected with my GitHub, so save a copy in GitHub. I will say Wildfire, and it's going to go in the ML folder. So ML folder, Wildfire ML folder, and that's where it's going to store. And ML, and that's where the California wildfire LightGBM. Next, we are going to use the xgboost Jupyter notebook where we are using xgboost. So here we are using xgboost classifier. Let me import all these libraries. Same design where we have already used the training, validation, and test source. We are reading the data set. So now we have training, validation, and test data set are already available. Features, we are defining exactly the same what we have done for LightGBM. Training columns, just to make sure that these are the columns we have. Now we are defining the xgboost classifier. Max depth is 10. Call sample byte tree is 0.8, learning rate 0.02, and estimators, I'm just using 100 here because if I use large number, it might take very long time and use all the available resources. So that's our xgboost classifier is defined. Now we are passing the training features and train and then verbose if you want to true. So that's a one option you have. Second, if you would want to use the training by passing the training as well as the evaluation, then you can use this option. So option 1, so this one is option 1 for without validation data set, and this is the option 2 with validation data set. So we are going to use the number 2 validation data set. Same logic. Let's start. It's going to run for 100 iteration. We didn't set the stopper or release stopping. So our training is completed for the 100 iterations. This one is the validation. If you would want to do based on cross validation, so that is also the optional. I will not run here, but you can also run. But let's try to, if these two are optional, if you would want to run the cross validation score. Here, based on the xgboost model we have just created, I will perform the prediction. So prediction is completed. Now we are going to create the AUC curve, which is similar to our LightGBM exercise. So our AUC score is about 78%, which is fairly low than what we have got at LightGBM, about 93%. Now we are going to print the ROC curve, and this is the ROC curve for our xgboost model. So this is just an example for you to just get an idea that if you are using LightGBM or if you are using xgboost, how you could build your model. You really need to go a little more deeper and try to build a better model by changing these estimators and then also adding the early stopping here. So that was the second example I wanted to show you to use the xgboost with our dataset which we have created. So let's save this and export this to GitHub as well. So let me export this to Wildfire, and it's going to be ML. And now CA Wildfire ML xgboost is also available. So we have xgboost, LightGBM. We both got these two Jupyter notebook for anybody would want to use and try, they can very easily. So here I already have the H2O library installed in my machine. Just for your information, I'm using Python 3.9, importing H2O and initializing the H2O instance. So H2O instance is started. So I will be using the H2O instance. First, for this scenario, I will be uploading all three files which we have created in this feature engineer exercise. So let me take data and upload a file. So I will be uploading the California train, and this is our CA fire training, and these are all our columns we have. Let's parse it. So our CA fire train is available. Next, upload, validation. Let's call it CA fire validation. Everything looks okay. Parse and upload. So now we have validation. Next, let's upload the test. Okay, so we have got all three. Fire is in teaser. This is our fire in the test. So let's reset it. Actually, I'm just reloading, but the data is still there. Data is already uploaded. So if you want to see the list of all frame, the test, train, and valid, these three frames are available. If we would want to start the machine learning, we could start by selecting a particular algorithm from here, or we can just select the training. So let's say this is our data set and fire is here, and if we would want to convert this to Boolean, right now it's integer, so it became Boolean. Let's try to reload this data. Install frame California train, and our fire is became the Boolean. Same thing we could do to validation. Fire, convert, so we got that. Same thing we could do to test. That's our fire integer. Let's convert it to Boolean. So reload. It just cleans up very quickly. Now we have data set. We can make sure fire first one, valid second, and the test also fire. All three is complete. Let's build the gradient boosting machine. So GBM. Training, we are going to use the train. Validation, we are going to use the validation data frame. Response column, we are going to use the fire. And rest, we are using all of these column as we have done earlier. And if you would want, we can actually do not use certain columns. So number of trees 15, depth, this is our learning rate 0.1. Let's use everything defined and go ahead and build our model. And our model is created. ROC for both training and validation looks 1. The H2O AutoML process is completed. So let's take a look at the model. And here are most of these model, and majority of these model, they had AUC 1, and here is the report about it. So you can get an idea about how you could start the H2O.ai AutoML process with our California wildfire data. There is a lot can be done, but I will just keep my project scope up to limited here, that how you could start the AutoML, and depending on what you would want to do, you can take this project to whatever length you would want to. So at this point, I will stop the machine learning process for California wildfire dataset, and let's go ahead and recap our learning, what we have completed in this tutorial. In today's tutorial, we started with our strategy, that how we could use the California wildfire dataset to combat the wildfire problem, which we have at yearly basis. So we learn how we could use our existing dataset and create a feature engineer dataset which could be used for the machine learning. So we use this strategy to generate our final dataset. After the strategy, we looked into a complete Jupyter notebook to ingest the California wildfire data, and after going through with various steps, finally we were able to generate our California wildfire data, which could be used for machine learning purposes. And we have also viewed this data into a map, so that we could see the wildfire hotspot all over in California. Once our feature engineer data was ready for machine learning, we used two different algorithms and libraries. So we used the LightGBM library to perform a classification task, and we completed that task. We learned the model metrics, which was almost around 90+% with the test data set, and we used the test data set, which was for year 2022 dataset. Similar to LightGBM, we have also used the xgboost and performed the similar classification task, where our performance was about 85%, around something close to that. After LightGBM and xgboost, we have also looked into the H2O.ai open source platform, and we used various algorithms such as gradient boosting, and we also tried the distributed random forest. And after these two, we have also tried the H2O.ai AutoML. So variety of libraries and variety of boosting algorithms we have used to build the machine learning model for our California wildfire data. Now, anyone who is looking this tutorial can extend this project to whatever length they want, because now you have idea how you could use California wildfire up-to-date dataset, and you can build a machine learning model to identify the hotspot as they are being appear in coming months, and you can notify, or you can build a general purpose application which anybody could use it. So we have concluded our tutorial, and it's great that you are here with me. I hope you have enjoyed the tutorial. I'm going to extend this content in this two-part tutorial, and I will try to build several other tutorials around it, such as using the wildfire dataset and visualizing it using Python backend and the core UI as well as the Chakra UI front end. So if you're interested in front-end development, you will find those content very helpful for you. I will also use this wildfire dataset and create a tutorial to show how you could use the Kepler.gl platform for visualizing this California wildfire data. The machine learning part I will definitely going to extend, and I will be using the California wildfire dataset along with the weather dataset, and combining these two datasets, I will be creating a new tutorial where we could extend the machine learning part to even more deeper and building a much more useful machine learning model. For now, we have concluded this second part of tutorial. It was great to have you in this journey, and I'm looking forward to seeing you in my next video. Until then, thank you. Thanks for your time. Please like it, share it, and subscribe it.